When we go to the certain collection implementations in Java, we will need to analyze their time complexities. Therefore, it will be proper to review how to measure the efficiency of algorithms in advance. In this video, we are going to define the concept of big O notation. First, let's start with the definition of algorithm. An algorithm is a finite sequence of steps for solving particular problem. When we need to analyze the speed of an algorithm, we need to find some way to do this properly. So what should we do? Maybe take a timer, hit start when the algorithm starts running and stop it after its execution finishes. There can be many factors in this measurement. Resulting time might depend on underlying operating system. Maybe some computers utilize more numbers of cores and computing time to run the algorithm way faster than other computers, even if the algorithm is not quite efficiently written. So instead of running time in milliseconds or seconds, we need to agree on some other common objective way of measurement, which will give general idea for the efficiency of an algorithm. One of the ways to analyze the speed of an algorithm is to look at the number of steps to perform an algorithm. This is called time complexity. Another measurement is memory complexity, which indicates how much memory it takes to run an algorithm. Big O notation describes the complexity of the algorithm using algebraic terms. So, when analyzing the time complexity, it considers the worst case for the number of steps the algorithm takes. Of course, we would like to observe best case scenario, but in reality, the best case is not regular. So it is better to be ready for the worst case scenario. We can also observe average case time complexity, but it still does not give us an upper bound, which is the absolute worst case result that we can get after running the algorithm. During our analysis, it can be an effective way to compare multiple algorithms using their worst-case scenarios, meaning that we will use big O notation. Let's say you are programming the vending machine that is applying the number of sugar scoops based on the user input. We can represent the algorithm with the following steps. First, get the cup of coffee. Next, take the spoon. Then scoop out the sugar with the spoon, add the sugar to the cup, and finally check if the quantity of sugar is equal to the user input value. If not, repeat the steps 3 and 4 until it will be. If we increase the number of sugars in coffee, we can see that steps will also increase, because we will need to scoop out the sugar and add it to the cup as many times as the number of sugars desired. If you only need one sugar, the algorithm will take 4 steps. If the user input for sugar is 2, then the algorithm will take 6 steps. For the input of 3, it will be 8, and so on. This dependency, as you can see, is linear. As the number of required scoops of sugar increases, so does the time of the steps performed in our coffee making algorithm. The function for the total number of steps will be 2n plus 2. Number of steps are determined by n. 2 will always be multiplied by n no matter what value the n has. So this 2 acts as a constant. For big O purpose, of course. And plus 2 will always be there and will not be affected by the value of n. Because of this, we can say that time complexity of this linear algorithm is big O of n. So n is what matters when defining number of steps. In this case, there are of course other time complexities: constant time, logarithmic log to the base of 2, linear, log linear, quadratic, and the order of time complexities are represented from the best to the worst on this picture. So the constant time is the fastest, meaning that operation only takes single action, no matter how many n's are in the input of the algorithm. And then it worsens as we get below to the quadratic in this case. This graphical representation of different algorithm time complexities is taken from FreeCodeCamp article. You can see the link in the resources section of the video. It shows how different time complexities look like. On the horizontal line, we have the number of elements, and on the vertical line, we got the number of operations or steps performed. As we can see, O of 1 is the best, and in general, anything above O of n times log n is considered undesirable time complexity. But of course, the certain situations might not be solved with the time complexity as fast as n times log n. So it always depends when assessing which time complexity is acceptable and which not. You can also see visually that as the number of elements increase, the growth rate of operations is extremely high in case of worsened time complexities, like for the quadratic and exponential time complexities. So this was an overview of what time complexity and in particular big O notation is. With this fundamental knowledge equipped, it will be much easier to continue our analysis of Java collections in terms of their speed for different operations applied. If you liked the video, please hit the like and subscribe buttons. Thank you for watching and stay tuned for the upcoming content.